So what a gorgeous day outside. I thought I'd kind of have a starting slide here that try to compete with the Aspen background. We'll talk more about this a little bit later, but this is Mount Sharp on Mars that we're approaching with the Curiosity rover, and so that'll be part of the talk today. Anyway, my name is Daniel Limonati. I work with the Jet Propulsion Lab, and we're going to chat about the Mars exploration program and what it's teaching us about how to do hard things. So we'll start, and hopefully you enjoy the ride. All right, so today, again, we will hit how the Mars exploration program has been doing very hard things for the last 15, 20 years, and some of the lessons learned that apply for similar complex endeavors on Earth. I'll also hit highlights of some of the science returned from Mars, and then talk about some of the stories, kind of some of the fun engineering and science challenges that we've had on the Curiosity rover specifically. I've been working on the Mars program since about 2001 on Spirit and Opportunity, and then since about 2004 on the Curiosity rover. So I've been doing this, working on Curiosity for a better part of 8 years. All right, so before I got started, or get started here, one thing I wanted to point out, just taking a step back, when I was getting ready to put this talk together, it's just kind of cool that we live, in the 21st century, and as citizens of this country and of the Earth, we have a place that people can work that's called the Mars Exploration Directorate, right? How cool is that? So I'm honored to be able to work for that directorate, and actually I work for you guys, right? You're the taxpayers. This is your program. And as I said before, what we do in the Mars Exploration Directorate is great things, and we've figured out a way to do that pretty consistently. Next, I'm going to show a video. I don't know if you guys, how many people were familiar with the Curiosity rover landing? August, okay, great. All right, so we have some fans here. August of 2012, close to a year ago. So I'll just show a video that kind of, in my mind, captures really well the awe and inspiration that the Mars program can kind of bring to the public when you do big things and you pull them off.
Things are looking good. Coming up on entry. Vehicle reports entry interface. At this time, it'll begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. We are standing by for guided start of guided entry.
One fun side note here is the one-way light time when this all was happening was about 17 minutes. And so even though there's lots of people and there's lots of tension, we really couldn't do anything about what was going on. It's just kind of makes it look dramatic and everything, but really we were just watching the show.
It is starting its first bank reversal. It is reporting that we are seeing G's on the order of 11 to 12 Hz.
So when we hit the Mars atmosphere, we hit it at about Mach 25.
We are now getting telemetry from Odyssey. We should have parachute deploy around Mach 1.7.
That's the parachute deploy close to Mach 2. And we actually took a picture of that parachute with another orbiter.
Teal has separated, we're on the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers descending.
That was
batch separation.
You actually see a view from a descent imager. We're taking 5 frame per second video during the landing.
We are in powered flight. We're at altitude of 1 kilometer descending. Standing by for sky crane. Sky crane is started.
Signal to us, you remain strong.
Touchdown confirmed. We're safe on Mars.
Fun time. So anyway, as you can see, that's a lot of people who put 8 years of blood, sweat, and tears into this program. The emotions run a little high. And apparently the rest of the world thought it was pretty cool. So
thumbnail.
Okay, anyway, so that was a really exciting time for me, my family, and the hundreds of people that worked on that project. One thing I forgot to mention, the Aspen Institute was generous. They gave me an hour for this talk. We have mics available, and so you guys can ask questions at any time. I'm not just going to wait till the end. I'll try to make sure I'm scanning the audience during the talk, and so as things come up, go ahead and just ask your questions, and we'll kind of work it in that way. You're also welcome to wait till the end. So, big picture, why did we go to Mars? What makes it worth it? We have 4 kind of grand objectives when we talk about Mars exploration. One is trying to understand the rise of life. So as everybody knows, right, Earth is this beautiful, habitable planet with just, flaunting its life, very, very happy place for life to evolve and exist. Mars, it turns out, it's one of the 3 other places in the solar system right now that we think life might have existed in the past or might even currently exist that hasn't been ruled out. The other places are Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. Mars is very close, and so it's an easy place to get to try to answer this question of, are we alone in the universe? And there was lots of talks. I think there was a talk last night. There's more talks later today on the space track that talk about life in the solar system, life in the universe, and what are the odds, of us being alone or not. And so clearly that's a big question. And not just did life arise on Mars, but let's say we find life on Mars or one of these other planets in the solar system, does it look the same as our life? Somehow were all the planets just kind of sharing bacteria effectively, because it turns out we actually share rocks between when impactors hit the Earth or Mars, little rocks go into space, and there's rocks that go between the planets and kind of share rocks and potentially share bacteria. And so if we find life on Mars, does it look the same as ours, or is it radically different and so indicative of a second genesis? And so one thing, obviously, if it's a second genesis, in my mind, that kind of blows the doors wide open on, if it independently evolved, then life is probably all over the place. At least simple single-cell life is probably all over the place in the universe. But we haven't answered that question yet. It's one of the big reasons we're going. The 2 next ones are kind of interrelated: climate change, geological evolution. One thing we do in planetology and space exploration is understand how other planets evolved and try to, both for its own sake and also as comparative planetology, to better understand how the Earth system works and how it might evolve in the future. Mars, a long time ago, we're getting more and more evidence, was very warm and wet. 3.5 billion years ago or so, we see evidence of running water on the planet. We've now found evidence, as I'll show you a little bit later, of actual neutral pH conditions, neutral pH water conditions. But then something happened over time where that water, the planet lost its water. It cooled down, it kind of became more and more stagnant. And so we want to understand what happened there. It's an end-member case of basically it's now kind of a deep freeze planet. Earth is kind of still just right. And as another example, we have Venus, which is a runaway greenhouse planet. And so we trying to understand these different planets helps us understand what might happen to ours in the future. Are there warnings for us for things to do or not to do to our planet? And then other interesting things, how did Mars as an end-member terrestrial planet, how did the volcanism evolve there? How did the crust evolve? How does it compare to ours? We have plate tectonics on Earth. Mars doesn't have any plate tectonics. Why is that? Things like that. One quick side note, these pictures, Mars is kind of blown up here. In reality, Mars is about half the size of Earth, rough numbers. And the surface area of Mars, though, because it has no oceans, is about equal to the surface area of the Earth. So there's a lot of land mass there. And then perhaps the long term, one of the most or the most important objective in my mind is it's a place to explore, right? As human beings, some people feel more strongly or less strongly about this. Obviously, since I work in space exploration, I feel pretty strongly about this. Human beings have been on the planet for a few 100,000 years, and the reason we now dominate the planet, for better or for worse, is because we had the urge, our ancestors had the urge and the curiosity to go and explore and walk over the next hill, cross the river. And so to the extent that we fill up this planet and run out of those places, I think it's not healthy for us as a species or as a civilization. And so Mars, as well as the rest of the solar system, and hopefully eventually the galaxy, provides us an opportunity to go other places and start new things. I know it sounds a little cliche, and some people are like, really? You think you're gonna get off planet? If you take the big picture view, I think within 100 or 200 years, right, if we survive the next 100 years, which are gonna be challenging, we're definitely on our way to becoming a multi-planet species, which will be very exciting for our kids and grandkids. Okay. Let's see. So I'm going to talk about the Mars program in context, kind of what missions has it spanned since the mid-90s. Before I get into that, I want to make sure people kind of have a little bit of a reference frame from a money perspective. Since this is the Aspen Institute, the Aspen Ideas Festival, a little bit of civic lesson. Does anybody know what the total world economic output is? Rough numbers. No. The what? Yeah, rough. So it's a giant number. It's about $70 to $75 trillion, right? If you add up China, the United States, all the developing countries, a ton of money, right? 70 with 10 or 12 zeros behind it. The US economy is about $15 trillion, and the federal budget, as most of you probably know, is about $3.5 trillion, right? So giant, giant numbers. The program that we're talking about runs as part of NASA. NASA is about a $17 billion a year operation right now. The Mars program runs on about $500 million a year. It sounds like big money, it is big money, but when you think about what do humans do on the scale of the planet, it's like 1/10,000th to 1/100,000th of the money, of the economic output of the planet. And so if you can't, some people bring up, very valid kind of social questions of, hey, we've got a lot of issues on Earth, why are we spending this money on NASA, on Mars exploration? And you could totally delete this program and everything I'm talking about and get rid of all those cool pictures and things. And it's not even the round-off error of the accounting of the budget of the country or of the planet. And so hopefully it makes sense that in this tiny, tiny percentage of the money that we have available, we spend a little bit of it looking forward and kind of keeping the dream alive for positive things in the future. So having said that, what did we actually spend? What have we done? Let's see. Okay. All right, so back in the 90s, we launched two spacecraft, mid-90s Mars Global Surveyor, which lasted about 11 years, and some of you might remember the Pathfinder mission and the little Sojourner rover. Those cost about $250 million a pop, and they worked. They did great things for us, effectively restarted the exploration of the red planet. One of the things that NASA did in the mid-90s under the administrator back then was try kind of a faster, better, cheaper approach. We had just gotten out of an era in the 80s and 90s where we had a lot of big flagship missions, and we spent, kind of billions of dollars, $4 billion sometimes on some of the big spacecraft. And the idea was, that's kind of a ton of money. Can we do it for less? And so these missions were some of the first in that class, and they did really good science for not so much, 250. And then, kind of continuing that experiment, we did two missions in the late 90s, Mars Climate Orbiter and Mars Polar Lander, that cost about $125 million a pop, right? The standard, hey, gee, you made it work for 250, I'm the manager, can you do it for half? And so this was an experiment, and it turns out you can't do it for half. 125 was really not enough. And Mars Climate Orbiter, basically we had a little, fundamentally it was not enough time for people to think about all the issues that might happen and go fix them, work them, not enough workforce. And Mars Climate Orbiter burned up in the atmosphere when it hit Mars, and then the Polar Lander basically didn't survive the landing, and we're not 100% sure of the root cause yet. So having had that experience where we kind of hit the far edge of, okay, there's definitely a too cheap, this is a hard problem, you need a little more money than that. Just for reference, I mean, today if you buy a 787 airplane, that's $200 million a copy that you have to pay Boeing for kind of a production thing. And so these are, unique spacecraft, $125 million is kind of pushing it. Okay, so then in the 2000s we had, through now, we've had a great run of successful missions, based on, a team of people that has been in existence largely since the mid-90s, and also more reasonable budgets. We had Mars Odyssey, which got to Mars in 2002. We had Spirit and Opportunity, which landed in 2004. The Phoenix lander, which landed in 2007. Mars Reconnaissance Orbiter, which is kind of a, I don't know, I want to say like 60s era spy spacecraft almost quality as far as imaging. Really amazing pictures that you'll see a couple of highlights of later, orbiting Mars. And these two are both still working. The Opportunity rover is still trucking around doing great things. And then the Europeans also got in the game, and they have a Mars Express spacecraft there. And then we landed, as you just saw, the Curiosity rover on Mars in 2012. And again, just to give you guys a sense for how much we're spending these days, the two Spirit and Opportunity rovers were about $800 million a pop for both of them. Curiosity, because it had so much more science and was doing so many, effectively the next level of capability, end-to-end cost was about $2.5 billion. So what's up next? We have a MAVEN spacecraft, which is an aeronomy or upper atmosphere explorer. It's launching in actually this year, November, and it'll help us figure out what happened to the Martian atmosphere. We know now, based on measurements from Curiosity and past missions, that it looks like the Martian atmosphere has thinned out by a factor of tens over the last few billion years. And so, why did that happen? Trying to understand that evolution is what that mission is trying to do. The Europeans are sending a trace gas orbiter to look for, in 2016, to mostly look for methane, right? And so why is methane interesting? Most of you guys probably know, right? There's two main things on Earth that generate methane. One is, in plain English, bacteria, farting, right? And so it's effectively a sign of life, right? It's a sign of metabolism and byproduct of energy creation by life forms on Earth. But there's also geological ways, water interacting with minerals under the Earth's crust and other things like that, that can release methane. And so both the Curiosity rover and this trace gas orbiter are trying to follow the methane story on Mars to help us see if it's maybe more biological or abiological in origin, which will be an exciting point. And then NASA is launching the InSight mission to Mars in 2016, which will kind of for the first time put a functioning seismometer on the planet and try to probe the deep interior of the planet, understand how the structure of the planet on the inside is different from the Earth and other terrestrial planets and the Moon. And then in 2018, the Europeans, actually both American and Russian contributions, are going to send a rover called ExoMars to the planet. And this rover is actually, unlike past NASA missions, is actually looking more directly for signs of life. We've been looking for signs of water and habitability, not looking for life directly. The Europeans are kind of going big and trying to see if they can find evidence of past or present life directly. And then in 2020, we've got effectively another copy of the Curiosity rover with a different science payload that we're in the middle of defining right now that will get launched and hopefully do good things again. So that's the near-term plan, and then out in the future, we've got ideas for what's going to happen, but it's a little bit murky, and it depends a lot on the results of these missions and funding profile, et cetera, what's going on. So any questions on program? Go ahead. You know what? Actually, I think they want to bring mics to you, so that this is being recorded, so they can hear your questions.
I was just wondering, is it more global cooperation about exploring Mars or competition?
Can you repeat the question, please?
Is there more global cooperation about the explorations or more global competition?
I would say more global cooperation in general, right? So we don't have enough money to kind of go it alone for the most part. And so there is a lot of working together, and I think we're trying to get better about not duplicating each other's missions and things like that. One thing that makes it hard, we have these arms trafficking regulations actually in the United States that make it hard for us to talk to some of our even allies, like Canada, the United Kingdom, the French, the guys that are out to get us, right? Those laws make it very hard for us to cooperate very deeply And it's actually a little bit of a challenge. We're trying to work that in Congress, but it's been a little bit of a challenge, and it actually makes some of the cooperation a little bit harder. But yeah, fundamentally, it's mostly cooperation. But on a personal note, there was a time when ExoMars was launching about the same time we were, and me internally, I was like, hey, we want to make sure that they don't scoop our science, right? And so, you do get a little bit competitive, but it's kind of friendly competition. Okay, so some of the fun stuff, right? The Dr. Seuss version, things we've seen and places we've been. Let's see, starting kind of with the most interesting, one of the fascinating things that we've learned, based on kind of relatively simple physics and theories of how, how water should behave on the planet, we didn't really think the water would be stable on the surface of Mars, and for the most part, it isn't. There are, however, we found a few places, actually many places on the planet where during the right time of year, it looks like there's things that could be water, like actually liquid water maybe seeping out of the ground like groundwater and coming out. We haven't proven that. We don't have a rover. Like, we need a little cliff bot to kind of rappel down some of these cliffs, and really check that out. But the orbital data seems to suggest that there might actually be running water here. And so this is kind of an interesting, eye-opening, super salty water that might actually be stable for some amount of time. And so we actually saw this. I don't have a picture of it, but on the Phoenix lander, it kicked up a bunch of ice and water droplets, and we actually watched water droplets kind of evolve on the lander legs over the time of that mission. And so, kind of a big deal result, because on Earth, anywhere there's water and an energy source, there's something that's alive. And so, this gives us some hope, and hopefully we'll get a mission to actually explore some of these spots. Here's some of the cool pictures from this kind of spy camera that has about 30 centimeter, half meter resolution. So we see a lot of features on Mars that are wind-carved, water-carved, deposited areas, that were maybe laid down by water over time or laid down by wind, sand dunes and things like that over time. So very cool kind of surface layering features. And we've even seen craters form. So we have all these orbiters, 3 different orbiters that are going around the planet taking pictures all the time. And we've had them there long enough now. We've basically had a permanent robotic presence at Mars since 1996. That places that used to just be flat, now we go back and take a picture again, and we'll see new craters, new holes in the ground. And they tell us, here's a little bit of ice or bright material that came out of this new crater. So it's kind of cool to see, the surface of the planet evolve over time with our missions that are there. Some of the fun things about Mars, here's a map of the basically topography of the planet. And we kind of have a better topographic map of the surface of Mars than we have of the Earth, because it doesn't have the pesky oceans that get in the way, right? And so we can actually map with laser altimeters the entire surface. And some fun features here, you kind of see Valles Marineris down here, which is the biggest canyon in the solar system. I think the Grand Canyon would kind of fit in a little corner of that guy. It's basically a giant stretch mark on the planet. And then there's these 4 huge volcanoes in the Tharsis Montes region. And this here, this big white dot, this is the white is high, blue is low, is Olympus Mons, this guy, which is 28 kilometers high. By far the biggest volcano, now dormant volcano, but volcano in the solar system. And the footprint of this volcano is about the size of Arizona. So it's this giant shield volcano. And other cool things that we get to do when you just take enough pictures over time is we actually caught in the polar region, in this layered polar terrain, you can see carbon dioxide and water ice here. The Mars Reconnaissance Orbiter took a high-resolution image of this cliff area and actually caught an avalanche kind of in process. So this is an avalanche actually happening on the surface of Mars. And so again, we have evidence that it's definitely a dynamic planet. Things are happening, changing the surface of Mars. And one of the more challenging things that for our rovers, as well as for eventual human explorers, is Mars sometimes gets globally enveloping dust storms, local dust storms, and sometimes they kind of blow up into world-encircling dust storms. And that's what moves, that kind of gives the whole planet this red hue. Is there's this kind of iron-bearing dust that's relatively uniformly distributed all over the planet by these dust storms. And so it can get very windy. And especially for the solar-powered rovers, we have to worry about that. And Opportunity actually and Spirit both survived one of these global dust storms. So that's kind of the view from space with our orbiters, and then this is the view from the folks on the ground, the rovers on the ground. Back in the 70s, we landed 2 Viking landers successfully on Mars. Kind of got this rock-strewn, relatively barren-looking terrain. 1997, as I mentioned earlier, Sojourner, this little tiny microwave-sized rover, part of the Pathfinder mission, landed and drove around. And then 2004, we landed the Mars Exploration Rover, Spirit and Opportunity. And this was kind of, if you kind of see a trend here, right? The places we'd been before were all kind of flat, rocky, kind of that was your dad's and mom's Mars. And then when we took the first pictures with Opportunity and saw these kind of flat plains, it was really kind of the beginning of a new era of Mars exploration where we were finally getting to new and different places on the planet. That was really cool. And then Curiosity, right, here's our big new rover. We've been on the surface for almost a year now. And we've actually done, I'll talk about this a little bit later, we've drilled into Mars for the first time ever as humans with robotic help. And one of the cool things is, I don't have a blow up of this picture, but you notice the powder, right? So the surface of the rock is red, right? Red rock is generally oxidized rock, oxidized iron, not necessarily very friendly for life or preserving signs of life. But the inside of this rock is gray, which is generally more indicative of a reducing environment, a neutral pH environment. And so this was kind of, even though we only drilled about 2 inches in the ground, this really was the mission payoff, is seeing this material, analyzing it with the instruments that are inside the spacecraft, and seeing that, confirming that the place that we landed, Gale Crater, which I'll talk about in a second, there are Earth bacteria and extremophiles today that if you took them back in time, 3-4 billion years ago when Mars was warmer and wetter, when these rocks were forming, they would be perfectly happy living in this environment, in the water that used to exist here, that we proved used to be here, and using the energy that's available in the rocks to kind of make a living. And so that was a big deal finding from our mission so far. And we're just kind of getting started. And so speaking of, right, so this is Mount Sharp. I'll show a picture a little bit later that provides a little context here. We landed in Gale Crater with Curiosity, and we are basically going to be driving from where we are now to the base of Mount Sharp over here, and then over time, climbing this 5-kilometer high mountain, which is going to be awesome. So it should be exciting. Kind of like going for a hike outside here, right, in Aspen. So I get to do that for a living. It's really cool. Okay, so a little bit of background, a little more on Mount Sharp and the Curiosity mission now. So we landed inside Gale Crater. This is actually kind of a zoom-in shot of a 100-kilometer diameter crater. Here is kind of the base of this giant mountain. Part of it, you can kind of see some of these outflows that look like maybe water outflows or wind. We're not sure yet. We're going to figure that out. And we are in this Glen Elg region right now. We're driving about 8 kilometers to this entry point at Mount Sharp, and then we're going to we're still trying to figure out, we've now planned our path, our little, if you guys like backpacking, right, this is what we do for a living. It's, again, really fun. As we've planned our backpacking trip from Glen Elg to Mount Sharp, and then once we get underway, we will start planning our backpacking trip from the base of the mountain into the mountain, which will be exciting. Some of the features here, you see these black dunes. These are black sand dunes. These are actually active dunes. We have time-lapse photographs that show these dunes kind of moving over the time span of a few years, and we'll probably sample some of this black dune material on our way to the base. And so then this circle area is kind of, the picture I showed at the beginning of the talk is that, right? So this is what we're going to be climbing. These are hundreds of feet high yardangs. If you go to like Mongolia, other places, there are similar, giant wind-eroded features. We think these are wind-eroded that exist on the Tibetan Plateau in Mongolia and other places. And so this exploring Mount Sharp is kind of like going to the Grand Canyon, right, where you can see all the layers. We see a lot of deposited layers. You see a lot of these linear features. And so with our instruments on the rover, with a drill, with our scoop and other instruments, we're going to be exploring these layers and effectively working through the history book that is Mars, right? And so that's what rocks tell us. It's kind of a mystery novel of the planet, and we'll be reading that mystery novel as we explore, just like early geologists did in the Grand Canyon and other places on Earth. And just for scale, from our vantage point here, again, this is like, on the order of 8 kilometers or more away. That little boulder, that little speck over there is a 2.5 meter wide, Shaquille O'Neal tall rover, right? So it's going to be kind of driving around, neck strain when we get to the spot checking it out. Any questions on this stuff so far? Go ahead, you, sir.
Who gets to name these features, and what's the process?
Let's see, so name the geological features? Or the rover, the spacecraft? Whatever. So actually, a little girl got to name Curiosity. So there was a nationwide, effectively, essay competition where kids from school got to submit their proposals, and there was a selection committee, and we picked Curiosity, and she actually got to, very articulate, very bright girl, came to the landing event at JPL. These other features, most of the names as far as the geology, we use informal names because there's actually a very formal process. There's an entity called the International Astronomical Federation that is actually in charge of naming things, and they have to bless the official names of things off of the Earth, right? And so that's a long process where you have to submit a name, like, hey, I think we should name this feature, whatever, Robert Goddard, or something, and it has to get approved effectively. And so in the meantime, when we work the mission, the scientists and engineers, we have to talk about things. We don't want to just say X or N, right? And so the informal name for the mountain right now is Mount Sharp. It actually has a formal name, I forget. And then we just kind of, the scientists just make lists of names. And as we drive around, like, hey, the theme for the next 2 weeks is whatever, the Viking exploration of, Greenland or something like that, right? And so we'll just pick names from that theme set, or the Spanish exploration of the Americas, and we'll just kind of pick from there. So, young lady, can you wait for the microphone, please? Yeah.
You mentioned bacteria able to live in the gray rock that's on Mars. How are we making absolutely sure that we are not introducing bacteria and various other life forms?
So that's a great question. So a couple things just to clarify. We don't have evidence that there's bacteria now. That statement was, hey, 3.5 billion years ago, Earth bacteria could live here, right? But yeah, your question is effective. We have a planetary protection requirement, right? So there's a person at NASA that's called the Planetary Protection Officer, and it's kind of another fun job title. And there's a two-way responsibility. One is, as you indicated, making sure we don't forward contaminate other planets, mostly for science preservation. And also, eventually, when we bring samples back, we want to make sure we don't do bad things, like if we bring a sample from Mars to Earth, that it doesn't maybe do bad things to us. And so we actually have requirements on how clean, how sterile the rover has to be. We bake out all kinds of hardware, wipe it down with alcohol, clean the rover. There's effectively like how many spores per meter squared are you allowed to have, and things like that. And so anyway, so that's all covered effectively in how we design and test the hardware and put it together. So, and since there isn't water right now, the ultraviolet environment on Mars is actually pretty harsh, and it actually kind of sterilizes a lot. Like if you're just exposed on the surface, it's not a happy place. Like most bacteria on Earth would kind of die there pretty quickly, and so it also has that kind of like belt and suspenders kind of thing, where the planet will most likely kill the stuff that's exposed. So go ahead. I guess with the red hat. Sorry.
Thanks. What's going to happen with the sequester? We've heard from Maven people. Uh-oh.
Yeah, so it's actually one of the big fights right now is trying to save the planetary science budget. And I think for 2013 it was okay. 2014, the budget is potentially going to get reduced because the NASA budget is fixed, and the administrator has to make some tough choices about the human exploration stuff versus planetary exploration. And there's a chance that the budget for the planetary side is going to go down a little bit, but that's still getting worked out. So I'm going to move along a little bit here. just because I got a few more slides, and maybe we can come back. And by the way, if you guys have questions I didn't answer, I've got all day. After 10 o'clock, we have to kind of wrap it up, but I can take questions on the side afterwards. I'm happy to do that when we let these guys set up for the next talk. Okay, so just speeding up a little bit. So kind of, we talked about these main reasons for going, and we've had these kind of vertically integrated approaches for exploring all of these questions. So we were looking for the water with a bunch of our missions, and check, we found water, lots of evidence for water. The Curiosity mission, Rover was the first one to really directly look for habitable zones, and first drill hole we made, check, we basically found evidence that, yeah, Mars in the past does look like it was habitable. So again, this long-term investment payoff has allowed us to do this. And so then the main thing that we're still trying to do is this really big question of, did life actually, the conditions were right, but did it actually start, and is it actually there now, right? That hasn't been answered yet, and that's still to go. Okay, so part of this talk is to hit lessons learned. One of the cool things that we do in the science program at not just for Mars, but solar system exploration in general, is the plans, right? The objectives are generated via pretty transparent, pretty democratic process with the science community and even other citizens if you want to get involved and just show up and make your case. They lay out 10, 20-year plans for, hey, for Mars, here are the big science questions, here's the objectives that we think we should hit in priority order, actionable down to, to hit this objective, you should have these kinds of instruments to answer that question, right? It's this really nice long-term plan. And then basically, once we have that in place, the funding is just trying to tick off the missions that are called out in these plans. The astronomy community does the same thing, and I think it's worked really well. And so, and I think that's an applicable thing for Earth-based projects is get a big group of stakeholders together, spend the time ironing out your objectives, making sure everybody's kind of got a chance to give their input, and then move out on that plan. Of course, being Mars, building support, making the missions interesting, engaging, inspiring, it's kind of easy for us, right? We do these awesome, really dramatic things landing on the planet, and so that definitely helps kind of get hard things done because it inspires people and it encourages them to give you more money for the future, right? That's a good thing. One thing we have found to be very important is, when you're doing hard things, even really, really smart people, the first time you do it, usually what kills us is a lack of imagination, failure to imagine all the possible things that can go wrong. And so even if you're a genius, you will miss things and it'll result in a bad day on the planet that you're trying to hit. And so, doing this consistently, doing it in a stable way where you have a workforce that you're training, workforce that hangs around because it doesn't take 25 years to get there. These projects get done in 3 to 8 years. It only takes a year to get to Mars. You can see the payoff. Now we have a cadre of experienced people that can do these hard things. And this last point is a little different from some of the other things you hear at the festival. I think a lot of people are saying, go big, go bold. The Mars program strategy has been kind of like, compared to some of the other things that are going, lay low, ask for a reasonable amount of money, and then just stay steady, right? Steady as she goes, so that you can build on your successes, build up this infrastructure, and people aren't trying to axe you all the time because you've got a ton of money tied up in the program. Okay, some quick things here. We got another 15 minutes or 20 minutes. So now I'm going to go into Curiosity a little bit more and talk about some of the subsystems real quick, and then some of the stories, some of the fun challenges we had getting this done. So this vehicle, as I said before, it's got about the wheelbase of a Humvee. It's about as long as a Mini Cooper, and it weighs 900 kilos. It's a giant vehicle. Maybe not for you guys, but for us, we're used to driving vehicles on Mars that are like half the size or a third the size or even smaller. Getting it to Mars, we launched about 4,000 kilos. To get 900 kilos to the surface of the planet, useful payload, we had to put 4,000 kilos on a trajectory to Mars, cruise stage, entry stage, parachute, all those things that I don't have time to get into. Some fun facts. It's a 6-wheel drive vehicle. Each of the wheels has its own DC electric motor. The corner wheels can steer, so we have 4-wheel steering on the corners. Each wheel, again, has its own motor, 10-amp brushless motor. And because we're on Mars, right, there's no tow truck. If you get into trouble, you can't call AAA, say, hey, sorry, can you guys tow us out of here? So we don't really go for speed. We put most of the power from those motors via nice high reduction gearboxes into torque. And so if you had kind of magic sticky wheels and you weren't traction limited, and if these wheels could really grab the dirt and not slip, all 6 wheels together put out about 3,000 foot-pounds of torque, which maybe doesn't mean a lot to you guys. Your car might have 150 to 500 foot-pounds of torque. An M1 tank, which weighs 60 tons and can go 40, 50 miles an hour, has about 3,800 foot-pounds of torque. And so if you put the M1 in neutral and you gave us magical wheels that don't slip, we can tow an M1 with this baby. But the downside is then when we push the pedal to the metal, we go 0.1 miles per hour. And so it's pretty slow. Phenomenal acceleration, but very small top speed. So anyway, some fun stuff there. There's this, the system that I was responsible for the last 4 years on the project was making sure this robotic arm, which weighs about 100 kilos, a little bit more than 200 pounds, worked well. It's got a tool set on the end. We have a drill. That's the backbone of this turret. There's 2 science instruments and some other sample processing hardware out here. A lot of stuff going on the turret. We have a UHF radio. We have our mast, which is a pan-tilt platform. It's got science cameras, high-definition video-capable, like 5 frames per second video-capable science cameras, which do a lot of cool things. And then we have our little Cyclops Eye death ray. Not really. It's a chem-cam instrument. The kids, of course, love this. This thing literally ablates rocks. And so basically what we do with this is up to about 7 meters away. And so maybe if I'm the rover, I could zap the exit sign with that laser. And what it does is it vaporizes the rock. And then we look at the emissions from that vapor, the plasma, with a spectrometer that's in here and inside the body. And we can tell the chemistry from about 7 to 9 meters away. And so it's a death ray, so if you didn't move for like a day and the thing kept shooting you, then maybe it could kill you. But it would just burn your skin a little bit. It's enough to vaporize a little like 0.5 millimeter diameter spot on the rock, but not enough to really hurt anybody. So my kids always ask, hey, did you see any Martians yet? Did you fire a laser at them, right? And it's like, no, we didn't. And if we did see them, we couldn't really defend ourselves. It'd be a little slow. It'd be like, hey, don't move for like the next 2 days so we can see where you are and then aim at you. So anyway, let's see, other fun stuff. We have a high gain antenna back here, to talk to Earth, but most of our data comes via this UHF link to actually the orbiters. And so the orbiters, there's this kind of big synergy going on between the landers that are on the planet sending most of their data to the orbiters, and then the orbiters with their big antennas sending the data back to the Earth. And then we have 10 different science instruments I'm not going to get into here, about 80 kilos of science instruments, which is like a factor of almost 40 more than the past rover missions have had, which is one of the reasons this was a little bit more expensive. Okay, so then one of the fun science challenges, just to give you a little perspective, it was landing site selection. So here's Gale Crater, on the order of 100, 150 kilometers in diameter. Here's Mount Sharp in the middle, this 5 kilometer high, 15,000 foot high feature. And what you see here, these ellipses are the landing ellipses. And so when we aim at Mars, which is typically the total trajectory is like from Earth is on the order of like 300 kilometers, right? And so we're aiming for an atmospheric window to then land in this spot that's maybe 20 kilometers or 40 kilometers, or actually like more like 20 kilometers, a box in the atmosphere that we have to hit from 300 million miles away to land on the planet. And we've gotten kind of better at doing that. Back in the 70s, with the system we had, we could kind of say, yeah, we'll aim for this spot, X marks the spot, and we'll land somewhere in this almost 200 kilometer long thing, right? So you had to find this gigantic parking lot. Right, there's always this tension between the engineering and science community where the scientists always wanted to go to the really cool places, the cliffs, the mountains, and you can't really do that when you need a parking spot that's as big as, like whatever, from LA to San Diego or something or more. And so over time, as our missions have progressed, we've gotten better and better at shrinking this landing ellipse. And with the Curiosity mission, because we actually do a guided entry. So we effectively did what Apollo did for reentry capsule guidance on Earth. And so when Apollo came back from the moon, they hit the atmosphere and they controlled their entry with a lift. They used the lift vector of the spacecraft and controlled their entry. We did the same thing with this mission, and we really shrunk this landing ellipse, which allowed us to kind of find this nice little tiny parking spot next to the mountain. And so the challenge from the science perspective was, it used to be that the engineers basically said, the scientists would come up with, here's all the places we want to go, and we would say, no, 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 and the last spot, like the one last spot that was left, they could kind of get to. And so effectively, the engineers chose the site at some level for them. With this mission and its capability, and hopefully we'll have this for future missions as well, effectively now when they have their list of here's all the places we want to go, we say, sure, check, 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 go. And now they have to decide, they're like, oh, wow, wait a second, now we have to fight amongst ourselves to finish picking this location. And so one of the cool processes I think the science community has is this, again, pretty open, merit-based approach to proposing landing sites, picking the landing sites, voting on the landing sites. And again, you guys, I could go in there, and if you made a strong enough case for it, you could propose the landing site, and it would effectively see if it gets voted off the island or not over the multi-year process that's used to pick these places. Any questions on this stuff? Go ahead.
Okay. Hi, I'm Gift. I'm a business scholar. My question was like 2 slides ago.
2 slides ago, sure. Okay.
Okay. I was just curious when you say making the missions interesting, engaging, and inspiring. How exactly do you do that?
So, couple ways. I mean, JPL and NASA actually have a significant PR machine, right? And so the missions intrinsically, most of them are, if you actually just talk about them and you actually get the word out to the public, they're kind of naturally exciting, right? And so a lot of times we don't have to do, it's not like we necessarily make design decisions for the most part that maximize this. With some exceptions, like this video camera that we actually had a video camera on the Curiosity rover that watched us do the descent, right? That was both science and kind of, I would say, PR, motivated. And then over time, we've just gotten better at getting the word out to the public and, setting up these events where, the public, the customer, right? You guys are one of the customers for these missions, gets to get engaged, see how we do these things, watch us do the landing. And also, we open it up to the science student community, usually over the course of the mission, and let kids get involved with helping operate the rover once in a while. That we did that with Spirit and Opportunity, things like that. Does that answer the question? Okay. Okay, and let's see, before I do this, back. Okay. All right, so the next story talks about our parachute development. And just to give you some numbers, again, as I said at the beginning, that parachute deploys at about Mach 2 and has to handle a load of about 65,000 pounds during the main snatch event. And it's not really supposed to look like that, right? That's a bad day on Mars when your parachute looks like that. It's a bad day on Earth if your parachute looks like that, if you're skydiving. We unfortunately don't have a backup chute. We can't look up and go, oh God, pull the backup. At that point, you're a new crater on Mars if that happens. And so, so this was 2007, and our parachute team, at the time we were supposed to launch in 2009. This was a little scary. And so, one of the things that we do, based on having tested these parachutes and things like that over a long time, is, we instrumented, the force, the forces that are exerted by the parachutes. We have load cells everywhere. We had high-speed video cameras that I'm not showing you. We had regular video cameras, like all over the place. This was the most documented parachute test in the history of mankind. And so, based on past lessons learned. And so all of that data, even though we don't think it's going to fail, we kind of cover ourselves in case it is going to fail and make sure that we have everything in place to figure out how it fails, if it does. And so after several months of looking through the data, and basically what happened here is part of the parachute inverted, and so it kind of flipped inside out and shredded itself. So the team figured out why, they made some adjustments to the deployment, and then fixed it. And so again, some other fun facts here. This is the world's biggest wind tunnel with the world's biggest parachute ever used off of planet Earth. It's about, from the attachment point to the end is like 120 feet. The parachute, when it's laid down on the ground, is about 68 feet in diameter. When it's kind of fluffed up and inflated, it's 50 feet in diameter. It's gigantic. And so even though we test this, and then of course we had many successful tests after this to make sure it would work, this is all subsonic on Earth, right? So that we kind of match, this wind tunnel can't do Mach 2. And we match the forces, but we can't match the wind speed. And so there's still a lot of pucker factor going on when you do this on Mars, because it's like $50 to $100 million to test it at Mach 2. You have to do it in the atmosphere. And so we rely on a lot of models and other things to make sure that we have confidence it's actually going to work on Mars. And so when it does, one of the reasons people are crying in that video is because like stuff like this could definitely go wrong, and it didn't, and it makes us very happy. Let's see, we're kind of wrapping up here. One of the other challenges, there's lots of challenges. One of the other ones was the drill development on this rover. So again, this is the first time the United States has put a drill on anything going off the planet since Apollo. And so this is one of the Apollo astronauts with the Apollo-era drill system, which was a multi-stem drill. So they had people in the loop that could drive this thing and apply some nice big forces and adjust to the realities on the ground. And even back then, the Apollo program had Apollo 11 through 17, right, minus 13. 13 didn't make it to the moon, but they had a bunch of missions that went to the surface, and it took them 3 generations of drill designs, right, because all the surprises they had with how the lunar regolith worked and things like that, to actually get it to meet its mission objective, which is to get cores from 2 meters deep down. And so, again, this is just, I'll use this later for comparison. This is the kind of a schematic of that Apollo drill. So we're trying to do the same thing with this rover. Here's the Curiosity rover, here's our front wheels, here's our 2-meter-long robotic arm, and the working end, the turret, right, which has the drill on it, trying to do the same thing that our Intrepid astronaut did in the Apollo era. And one thing we found is it takes a lot of trial and error. You really gotta, as you hear from other, this kind of applies to lots of domains, build and test a lot, fail early, see how it breaks, just like with the parachute, to try to get confidence in your design. We had, even after spending years, testing this rock and this drill in hundreds of different kinds of rocks and things like that, we had some issues in the final drill design that we had to work, but using kind of our ingenuity, we overcame even the final challenges that we had, and now this drill does what it's supposed to do on Mars and is working great. Just kind of for reference, here's kind of roughly to scale the Curiosity drill compared to the bigger Apollo drill. So since we hadn't done this in literally 30 or 40 years, we didn't want to bite off more than we could chew, so we kind of started small. Future missions will hopefully expand on this and be able to go deeper in the ground on Mars. Okay, so last couple minutes here. So one thing I wanted to kind of point out, if you remember that program slide where I was showing all the missions and what happened with Mars Polar Lander and Mars Climate Orbiter, I'll get to you in a second, sir. So the NASA as an agency had this kind of rational strategy. Hey, our missions are getting too expensive. Let's take a little more risk and maybe double the number of missions we can do. And if a few of them fail, that's okay, because we're still ahead, right? If 20% of the missions fail, but we're flying twice as many, you're still winning, right? But I don't know if you guys remember the late 90s, right? So when those spacecraft failed, right, the press would put out, there's cartoons of JPL folks at the blackboard as monkeys that can't do math, right? And things like that. And so, we didn't really communicate, I think, to the media, to the public, to Congress, that strategy effectively. And so you get lampooned, people don't really like to see the failure. And so the key lesson learned there is, if you're taking a strategic tack that isn't really in line with the environment or the stakeholders, maybe that's just a bad idea, right? And so after what happened at NASA after the late 90s was we went back to, okay, people don't like it when we take these chances. Let's spend more money per mission and get it done right, which is what I've been talking about. But again, now they cost tens, like $1 billion+ often, right, to do the highly capable things. So that's the side of that trade. So the other thing I want to talk about here is, as you do this over time, you develop a culture of how to do hard things, how to do scary things. That's very important. And a huge part of that is risk identification, thinking through the worst case scenarios, staying up all night, staring at the ceiling, thinking about what can go wrong with your system, coming up with tests for that to see if it actually will go wrong or not. And coming up with a list, like, hey, as engineers, what we do for the project manager, system engineers, we're like, hey, here's the 100 things that I think can go wrong with my subsystem or my system, kind of in priority order of likelihood, consequence, the highest likelihood, highest consequence things. We have these risk matrices we put together, and then, the project has money, like significant amounts of money set aside to then buy down those risks, right? They ask us questions, okay, if you want to eliminate that risk, can we do something about it? Can we do a test? Can we build the hardware a little differently? And so there's this very rigorous process that we employ in the space industry, that the Defense Department, other people, the energy companies use to do hard things successfully. And just as a quick aside, I'm going to jump on my soapbox for a second here. Having this experience, when I look at how sometimes we do other things as a society, I get a little almost flabbergasted. If you came to a NASA or some other program manager and said, hey, you have a $74 trillion world economy. There are 7 billion people on it. And so climate change, even if you're a skeptic, right? Let's say there's a 5% chance of the worst case scenario happening, for example, right? Would you spend any money trying to mitigate that risk, right? If you're us, the way we do things, you'd say, wow, if there's whatever the probability is, 5%, 10%, who knows what it is. If that's a significant chance of some really bad thing happening, is it reasonable to spend a few $100 billion, maybe even $1 trillion, right, of the 74 trillion that the world puts out to try to manage that? The answer from the community of folks who do hard things all the time would clearly be, yeah, that's worth it. You want to get to the 22nd century in one piece and be happy that you made it through this difficult time. So anyway, it's interesting, when folks like us look at how we do things in society, and it's sometimes hard to understand why people don't want to, even if it's not a sure thing, don't do something, a little more actively to mitigate things. Anyway, I think I'm kind of out of time here. Some of these other things are kind of self-explanatory. Obviously, one thing you'll hear a lot is, no matter how much money you have to have knowledgeable, skilled people, passionate people that care about what they're doing. In our case, people that really don't want it to be their fault if something goes bad on Mars. And that's really a huge part of making these happen and building this team. Having hundreds of people that work together, cohesively takes a while. It takes time to build that up, stable environment to build that up, and then working complexity management. But I'm not going to talk about that. A little bit out of time here. So just to the end, again, this is your program. And so I encourage you guys, right? We all work on this together. You guys help pay for this. If you're interested to follow the Mars program and Curiosity at this website, this is where the Mars program website, this is the Curiosity mission website. You can follow Curiosity on Twitter, on Facebook. And then for those people that have spare time, there's a lot of citizen science things going on in the astronomy world and other places. You can go to Be a Martian and actually help do some of the science. So we'll take a couple of questions here. Actually, we're done. Okay, so we have to wrap up. But you know what? If you guys want to come off the side, I'm happy to talk to you.